Hello everyone, and welcome back to the second video here for our chi-square testing. In this particular one, we're going to cover the chi-square test of independence, which is a slightly different test, and we're going to talk about how to recognize whether it's a goodness of fit or an independence test. So let's jump right into it and get rolling. Now, a chi-square test of independence, if you remember from probability, we talked about independent events. That's what we're testing here. So we're testing, are two events truly independent? And so, how is it different from the other chi-square tests? This is the other really important thing here. Here, you're going to notice that you're given one population, but they're split into two categories. So instead of just having a row or a column like we had in the moose question, what you're going to have is a two-way table. You're going to have some rows and you're going to have some columns going across the top. And so one of the biggest giveaways that this is an independence test is that you're going to have a two-way table. The other important thing is that this is also sometimes called a test of association. So if you are looking for some giveaway wording for whether or not this is going to be a test of independence, what you're looking for are the words, is there an association between these two things? So, how do we calculate our expected counts now? Now, there is a very specific formula for it. Now, if you remember from probability, if events are independent, we said the probability of A times the probability of B was the probability of A and B. And so this is where the formula comes from. And so in this particular case, the probability, right, in this case, if we go the probability of being in a row times the probability of being in a column should give me the probability of being in that one particular cell, right? Row and column is that one particular cell that we're in. So the probability of being in a row now, this is the row total over the total times the column total over the total. And so now to get the actual expected number, that's my probability, I'm going to multiply that by my total sample size again. And so what this ends up being is that my expected is equal to the row total times the column total over the total sample size. This formula is very important for the multiple choice section. If you remember from class, with a chi-square two-way table test, when you're using the matrices on your calculator, the calculator will calculate the expected for you and automatically put it in matrix B. So this isn't something you have to worry about necessarily for the free response section. But oftentimes on multiple choice questions, it'll say, what is the correct formula for the expected counts? And so, knowing this, as opposed to having to do the test on your calculator and then see which formula matches up to give you the right number, if you remember this, life is easy and life is good. So let's take a look at an example here. Right, so this question, yes, I understand, is kind of old here. But it's a good question. And honestly, the chi-square doesn't show up super often on the free response section. And so for this particular one, here's what we have to do for this kind of thing, right? Oops, I'm on the eraser. So for my hypotheses, we're always going to assume independence. So for here, we're going to say that gender and response, right, are independent. Or the other wording you may see is have no association. But because this particular one says response is dependent on gender, I'm going to specifically write this as independent and dependent. And so here, for my alternative then, I'm going to say gender and response are dependent. Easy. Now, my assumptions here are the same as a goodness of fit. So I need a random sample, which I have. The problem up here, if I quote, it says a random sample of 200. Right, that's very important. So this is good. And now for all of my expected being greater than or equal to 5, here's what I typically do for this one is I'm going to make my own table here to show all of the expected counts. Now I believe we had, what do we have here? 5. So now to show my expected counts, if I did this in my calculator, this is 13.5. This is 16.5. This one's 18. This is 22. The same here. This is 22.5. This is 27.5. And then this is also 18 and 22, which probably isn't surprising, given that when you look at these numbers up here, right, it was the same 40 total. And so if it's going to be independent, that would remain the same. And then I show that all of these are greater than or equal to 5, so I'm good to go. And now when I do my chi-square test here, what I get is a chi-square value of 8.9, 8.923. And now for the degrees of freedom in an independence test, it's rows minus 1 times columns minus 1. That is my formula. And so in this case, I believe I have 2 rows, so that's 1. I have 5 columns, so that's 4. I have 4 degrees of freedom, and this gives me a p-value of 0.063. And so if I look back at the problem, here, notice it doesn't give you a significance level, but if you remember what we talked about a while ago, for older problems like pre-2009, 2010, 0.05 was the standard significance level. So if they didn't give you one, you assumed 0.05. So in this particular case, since p equals 0.063 is greater than 0.05, we do not reject. In this particular example, we do not have evidence that the response to the statement is dependent on gender. So I hope that was helpful, and I'll see you guys in the next one. Bye.